All right, we are going to be going over Unit 4, which is best fit models, correlation coefficient, and residuals. We're going to start with best fit models. So we've talked about two different models of best fit, linear and exponential. So first, we're going to look at linear regression, or a line of best fit. So for a line of best fit, you have three different representations of a linear function. You have the table, scatter plots, and the equation. So for a table to be linear, or if you're looking at a table and you want to know if it's linear, the y values are going to be changing by adding or subtracting about the same amount each time. So your y values will either be increasing by about the same number or decreasing by about the same number. The scatter plot for a linear function is going to look like a straight line. It might not be exactly a straight line, but it will look like the pattern of a line. Then we have three different types of relationships or correlations between those x and y values. So your scatter plot will either be completely random, and we would say that's weak or no correlation. It can look like the pattern of a line with a positive slope. We would call that a strong positive relationship. Or it could have the pattern of a line with a negative slope, and we would call that strong negative. Then for the equation of a linear function, we know this, it's y equals mx plus b. And in Desmos, you have to type in that Desmos language version of that equation. So when you type a table into Desmos, I'll show you right here just real quickly. When you add a table, it shows you x1 and y1. So in Desmos, when you want to know the line of best fit from a table, you have to type in y1 squiggle mx1 plus b. Then the m that it gives you in Desmos, that tells you the slope or the constant rate of change. And b is the y-intercept or the initial value of those data points. All right, so let's do an example of finding a line of best fit from a table. I've already got my table added in Desmos. I'll show you again. It's plus, and then click on the table button. And then you just type in all of your x and y values. I've got my table in here now. And now I want to know what is the line of best fit for these data points. So in a new box in Desmos, we type y1, go to ABC to get your squiggle, and then mx1 plus b. Now this tells me some information down here, the statistics that we're looking at when we get to correlation coefficient. That's the R that we're looking at. But to write the equation, we just need the parameters. M and b. M that we get in Desmos is 0.5 about. It's approximately 0.5. And B is approximately 23. So that matches up with this equation here, 0.5x plus 23. Next, we have our exponential regression model. So that is when you have a model that looks like it is more fit towards an exponential function versus a linear function. So first, we're going to look at the table for an exponential model and how you know when it would be exponential versus when it would be linear. So the y values are going to be changing by multiplying or dividing about the same amount each time. It looks like they're around about multiplying by about the same number or dividing by about the same number each time. That's for your y values. Then the scatter plot or the graph, you have three options for what that could look like as far as the relationship between x and y. So again, if it is just completely scattered about randomly, we say that is weak or no correlation, so it's not linear or exponential. There is no real relationship between x and y. We've also talked about if your points seem to be moving upward, but they're not necessarily in a straight line or forming the pattern of a line, they're more forming a J shape. We would say that is a strong positive relationship that is exponential. And on the opposite side of that, we would have points that are moving downward but in an L shape instead of in a straight line. we would say that's a strong negative exponential relationship. And finally, the equation of an exponential function is y equals a times b to the power x. So in Desmos, again, we have to make sure that we're using that Desmos language to tell it that we want an exponential function instead of a linear function. So again, if you have a table, you click plus, add your table, and then in Desmos you would type in y1 squiggle a times b to the power xy. A in this equation for an exponential is always the initial value or the y-intercept, and b is the base. Now the base tells you the number that's being multiplied over and over. So I'm going to take you back to the table. If your y values, for example, let's say your y values were 3, let's say your y values are 3 and then 6, 12. So if this is the case, then my exponential function, or my base for my exponential function, 3 to 6 multiplied times 2. 6 to 12 multiplied times 2. So this number is my base. So that is what goes into my equation here. Okay, now let's do an example of an exponential best fit model. So we have a table here. I'm going to put these values into Desmos. I've already got my table up, and we're typing in, notice where your x's and y's are in this table that's going sideways. Got to be careful there. All right, I've got my table done, and when I look at these values, I can see that to get from 0.75 to 2.3 and from 2.3 to 7.8, 7.8 to 21.4, and so on, those numbers are not increasing by a constant amount. So making the jump from 2.3 to 7.8 is not the same as adding about the same number to get from 7.8 to 21.4. So that clues me in that this is probably going to be exponential. So we are going to set up an exponential best fit model in Desmos. So we need y1 squiggle a, I'm going to put parentheses, b, and then we're going to raise that to the power by clicking this button here that says a to the power b. That gives us an exponent, and our exponent needs to be x1. Then I'm going to click log mode. Okay, we need to click log mode because that gives us more accurate numbers down at the bottom. It gives us what we need for a, b, and the r value. Okay, so to write this equation, we're going to take our y equals a times b to the power x, and we're just going to take a and b and plug them in. So a is about 2.34, b is about 3.0. So the function that has the correct a and b values that we need are option B. A is 2.34, B is 3.01. I made a mistake. There we go. 3.01, so that would be B. So this part where it says is approximately tripling for each increase in x, this is where this comes in. So I can see that to get from 0.75 to 0.23, it's not exactly tripling, but from 7.8 to 21.4, that is pretty close to tripling. 21 to 60 is very close to tripling. So where it says approximately tripling, that means approximately multiplying by 3. Again, it's not exactly, but that's why we're using best fit, because it's not exact, but it's very close. Now we're going to talk about correlation coefficient. Correlation coefficient is another term for the word R value. So R value comes in Desmos. If you'll look here where it says R equals 0.9994, that is our correlation coefficient for the example we just did with that exponential table. So first of all, this word R value, the R stands for the word residual, which we're going to talk about next, but it gives us a sense of how strong the relationship is between X and Y. So in the example we just did, we got the R value of 0.994. So we're going to talk about what that number actually means in just a second. Okay, so first of all, the R value, it's a number that gives the strength and direction of the relationship between two variables. So it tells you if it's strong or weak, and the direction, it means that it's positive or it's negative. So that R value, R, is always between -1 and +1. So if we created kind of a number line or a scale from -1 to +1, then you can see here 0 would definitely be in the middle, and anything less than 0 is a negative correlation, anything greater than 0 is a positive correlation. Now the closer you are to -1 and the closer you are to +1, the stronger that relationship is. The closer you are to 0, the weaker it is. So for example, I'm going to give you a few things that you can look at to see. So close to -1 will be -0.9, -0.8, -0.7, and so on. Closer to 0 would be -0.1, -0.2, and so on. Then closer to +1 would be +0.9, +0.8, +0.7, and closer to 0 would be 0.1, 0.2, 0.3. You're not likely to see very many here in the middle. Anytime we're using best fit, it's going to be either a strong or a weak. So here's a couple of examples that we'll talk through. If you have an R value of -0.98, first of all, this is a negative number, so it is going to be a negative correlation. But since it has 0.9, 0.9 is very close to -1. So we would say that is strong. So this would be a strong negative correlation. Now example 2, 0.23. This is positive, but 0.2 is very close to 0. So this is going to be weak. But since it's positive, it's still positive. The next question you might have is, how do I find this R value? Where does it come from? When you fit a table to a best fit equation, then you will get an R value when you click log mode if you're an exponential, or you'll get an R value when you type in your linear best fit model. So when you type these into Desmos after you put your table in, it gives you an R value. So you can see over on my Desmos screen where it says R equals 0.9994, that is my R value. So this exponential function we have has a strong positive correlation. So that means that those data points that I put in this table up here, they are very, very close to fitting a exponential model. Finally, we're going to talk about residuals. So residuals are the difference between the actual Y value and the predicted Y value for a set of data. So you can see in this diagram here, if we have some actual points, say they're from a table, and we put them on a graph, and those are our actual points, and then we get a line of best fit, then the residual is the difference or the distance vertically between the actual point and the predicted Y value on the line of best fit. So this blue line represents the residual or the distance between the actual Y value and the predicted Y value. The process for finding a residual is pretty simple. It's just a matter of subtracting the predicted Y value from the actual Y value. In other words, the residual is equal to the actual Y value minus the predicted Y value. So to find the actual y value, that's going to be on your graph or in the table that you were given. So the actual y value of someone with a height of 66 inches, the actual y value is 9.5. So the actual circumference is 9.5. We need to know the predicted circumference so that we can subtract 9.5 minus whatever the predicted is. So to find the predicted circumference, we have to use a line of best fit. So I've got my table in Desmos. I've got my y1 squiggle mx1 plus b in Desmos. That tells me m and b so that I can write the equation. So m and b. Now I need to know the predicted circumference. So the predicted y value if x is 66. So I'm going to take my equation, substitute 66 for x, and see what that is equal to. So in Desmos, I have 0.160714. I plugged in 66 and subtract 1.20714. And that gives us a value of 9.399984. Okay, so we are going to use this predicted y value. Oops. And we're going to subtract it from the actual y value. The residual is going to be equal to the actual y value, 9.5, minus the predicted, 9.399984. Okay, so 9.5 minus 9.399984 is about 0.1. So if we round that, it's about 0.1. That is how you find the residual. This is the difference between the actual value of y minus the predicted value of y when someone is 66 inches tall. Now let's look at an example that is a little bit different. So the height h in centimeters of a certain plant t days after it is planted can be described by this linear model. If the plant's actual height was 6 centimeters on day 5, what is the residual? So we know that the residual is the actual minus the predicted, and we know that the actual height on day 5 is 6 centimeters. So we want to know what is the predicted height on day 5 and subtract the actual height minus the predicted height. So to find the predicted height, we're going to substitute in day 5 into the equation that was given to us. So we don't have to find the line of best fit, that was already given to us. So if t is 5, so t is the time in days. So if t is 5, what would the height be? So in Desmos, I'm going to substitute in 1.20 times 5 plus 0.14, and that is equal to 6.14. Now we just have to subtract what is the actual, which was 6, minus the predicted, which is 6.14. So to find that value, that would be 6 minus 6.14. So this is the residual. The residual is equal to 6 minus 6.14, and that is negative 0.14. So this means that this plant was 0.14 centimeters less than what it was predicted to be.